All right, now we enter module 7. It's the part 2 for planning and control. In the previous module, we have talked about different technologies used in planning and control. And in this module, we focus on 3 parts: behavior, decision, motion planning, and feedback controls, which are the core of this planning and control module. First of all, what is behavior decisions? It's actually a module to generate a set of commands to define the behavior of your car. By behavior, I mean high-level behavior. One behavior would be to switch lane from your current lane to the left lane, or to overtake the next car, or the car on the next lane, and so on. These are the behavior decisions. And then how do we model this thing? Because it's very complex situations. Because the road, you have so many different cars, so many different situations. You might be on an intersection, or you might be on a freeway intersection, and so on. So the highest level of abstraction, we need to define all these scenarios. So we break down all the possible scenarios into different layers, and that's what we do. If we look at the figure here, we have different layers of scenarios. It may be on a traffic interchange point. There's a scenario that defines your own master vehicle, how it should behave. And then we have a scenario for example, for four-way intersection, and we have a scenario for lane split, and so on. And then for each of these scenario, we have what we call the synthetic decisions. And then the synthetic decision, for example, it's a sequence of individual actions you should take to make that happen. For example, you switch from the current lane to the next lane. That's a synthetic decision. And then the synthetic decision can be further broken down into individual decisions. For example, move to the left, that's an individual decision. So we have a hierarchy of different decisions, from the scenario to the synthetic decision, and then from the synthetic decision to the individual decision. That's how we model the whole environment. And then the input to this module is actually the output of the routing module we talked about in the previous section. Such that it's a sequence of lanes, and then localization results and obstacle and so on. They are all fed into this behavior decision module. And then the behavior decision module then puts these into different scenarios. Then the scenario is broken down into synthetic decisions, and then further broken down into individual decisions. And then these individual decisions then are communicated to the module below it, which is motion planning. So again, to recap a little bit, the behavioral decisions, they generate behavior plans for the vehicle. And then we enter the next part of this planning control, which is motion planning. The only purpose of motion planning is actually to generate, based on the behavior of the car, to generate a set of actions, a set of commands for the car to execute. So for example, to start with that, we need a model of the car. How do we model the car to plan its motion? The usual tool we use is called SL coordination system. For the world coordinate, when you travel on the road, you use X and Y, because you don't actually have the height information on the road. So you use X and Y. But for car planning, we use the SL coordination system. S here is the distance traveled along the tangential direction. You can see the figure down here is the SL figure of the vehicle, and the L is the lateral distance, which is perpendicular to the S the S direction. So we generate motion plans using this SL graph, and then based on this we generate a trajectory, which is, you can see on the right hand side of the figure. It has many different trajectory to choose from. Then choose the most efficient one. By efficient, I mean you don't make a huge turn such that we are applying to the comfortableness constraint and so on. So we usually use dynamic programming to generate such motion planning trajectory plans. And then once we have this trajectory plan, we will communicate this plan to the module below it, which is the feedback control. So now we are at the feedback control. First, to do a feedback control, we need a model for the vehicle itself. So the vehicle usually have 4 wheels, but to keep things simple, we use a bicycle model, such that we assume that the vehicle has 2 rigid parts, the front view and the rear views. So that's why it's called a bicycle model, because it has only 2 parts. And then for so now we have a model for the vehicle. We need to do the actual feedback control algorithm. It's called PID. So PID stands for proportional, integral, and derivative control methods. So actually have three parts: the P part, the I part, and the D part. And the P part actually accounts for the current error. So we give a control command, it executes, but there's some discrepancy between them. It's the current error. The I part, the integral part, is accounting for the past errors. And the derivative part is going to account for potential future error. By combining all this information together, we can actually optimize the whole control loop and reduce the execution error and make it very smooth. And so that's the feedback control for autonomous vehicles. So by now we have covered all different pieces of planning and control pipeline. And then actually we have covered all the pieces of the algorithm part for autonomous driving. In the next module, we're going to talk about client system. How do we combine all these algorithm modules together onto one piece of physical machine and execute them smoothly and robustly? So let's focus on client systems in the next module.